Have you ever wondered what makes recurrent neural networks different from traditional neural networks? Why are they called recurrent? And how do they fit into the broader picture of machine learning? To unravel this mystery, let's begin by understanding the basics of traditional neural networks. Imagine these as a series of interconnected layers of neurons with data flowing in one direction, from the input layer, through the hidden layers where all the processing occurs, and finally to the output layer. These networks are quite proficient at tasks such as classification and regression. However, they have one significant limitation. They process each input independently, without considering the sequence or context of the data. Output. Enter recurrent neural networks, or RNNs. They were designed specifically to overcome this limitation. RNNs are equipped with a unique feature, an internal memory. This allows them to retain information from previous inputs in a sequence, making them ideal for tasks requiring the understanding of context or order of data, such as language modeling, speech recognition, and time series forecasting. Imagine a simple RNN structure where each neuron sends output not only forward to the next layer but also back to itself. This looping mechanism allows the network to accumulate information as it progresses through the sequence. In practice, this is not a literal loop but an unfolding of the network over each time step. This shared parameter approach, or weight sharing, makes RNNs particularly efficient for handling sequences of variable length. Output. So when we compare RNNs to traditional neural networks, three key differences stand out. First, the memory. RNNs can hold information across time steps, while traditional networks process each input independently. Second, the type of data. RNNs are inherently designed for sequential data, making them better suited for tasks like natural language processing or time series analysis. And third, weight sharing. RNNs use the same weights across all time steps, making them more efficient and reducing the number of parameters that need to be learned. However, RNNs are not without their challenges. The most notable one is the difficulty in learning long-range dependencies due to the vanishing gradient problem, where the contribution of information decays geometrically over time. This makes it hard for standard RNNs to remember long sequences, but don't worry, machine learning scientists have developed more sophisticated versions of RNNs, such as long short-term memory networks, or LSTMs, and gated recurrent units, or GRUs. These models introduce mechanisms to better control the flow of information, allowing them to remember information for longer periods without suffering from the vanishing gradient problem. So, to wrap up, RNNs are a powerful and efficient tool for handling sequential data, equipped with a form of memory that allows them to understand the context and order of the data. While they do have their challenges, advancements in the field are continuously improving their ability to handle longer sequences and more complex tasks. Now, isn't that fascinating?